Hello and welcome back, guys. In this little video, I'm going to be talking about this week's exam problem. And this is an exam 2 problem, which means that we are actually allowed to use our CAS calculators to answer these questions going forward. So to start out with, we're asking about stationary points. We have been given a function. Now, before you answer any question like this on an exam, if you have access to a CAS calculator and they define a formula or a function, I would recommend right off the bat just defining it using your CAS calculator. To do that, we can go Action, Command, Define, and I'm going to type in define g of x is equal to 4 times x. Now, for the x's, I'm going to use this power button. So x to the power of 3 minus 3 times x to the power of 4. Just, I prefer it's the up arrow thing that you can use. Otherwise, we get this gx is equal to this. Awesome. The question asks, what are the coordinates of the stationary points? Stationary points are things that look like this, or this. Those are called maxima, minima, or stationary points of inflection. They're the 3 types that we'll be looking at this year. This is essentially when the gradient of the curve is equal to 0. So if you remember stuff about the derivative, you can calculate the derivative, find when the gradient is equal to 0, and then work out what's the value of y for those values of x. We haven't learned about that yet, so just using the CAS calculator to answer this, we can just jump over here and go into the graphs and calculator screen, type in g of x, because I've actually already defined it. I can now click tick and click this button here. That sketches a graph of our particular function, which is this one here. Now, looking at this graph, we can see that it appears to have a stationary point of inflection and a maximum turning point. We can find the coordinates of these things by going analysis, gsolve, fmax. That gives us our maximum, 1, 1, which is a local maximum, we should mention, just to use the correct terminology. And then we can work out what this other one is. I can go analysis gsolve. That's a point of inflection. I just click inflection and it locates it for me. So at 0, 0, we have a stationary point of inflection. Awesome. So that's how we can label those. Fantastic. All right. So now we need to sketch the graph. Now, again, this is a tech active assessment, so we could just go about putting these things in. It's just really important when VCAR gives you these curves that look like this, we need to make sure that we use the grid lines accurately. So I would just start by actually just putting in those values that we know. We know that up here we have a stationary point of inflection at 1, 1. A maximum turning point at 1, 1. There's a stationary point of inflection at 0, 0. And, well, what's the x-intercept? Not sure. We could use analysis gsolve root to find that. And then I can click over here and I can see that it's 1 1/3. Yep. Or we can go over here and go back to our main screen and I can just go, all right, so I'm trying to find essentially the x-intercepts. That's when x is equal to 0, right? It's when y is equal to 0. Never mind. So when does y equal 0 for the function g of x? Well, we could do that by hand. So we could say that's equal to 4x cubed minus 3x to the 4. I could factor out the x cubed there. We get this, and we can see that our values for x are therefore going to be x equals 0 or 4/3. So that's when this is equal to 0. So that's when x is 0. Or when is this equal to 0? Well, that's when x is equal to 4/3. Or we can just jump over to our CAS calculator. We can go Action, Advanced Solve, and we can go solve for 0 equals g of x, comma x. Gives us our answers. So 4/3 and 0. So let's put them in here. We have our 0, also happens to be a stationary point of inflection, and also now we have 4/3 0. Okay, so those are our points that we need to know about. Fantastic. All right, so now we need to go about sketching this. Now, this function here, we can see it's got a negative leading coefficient. And because that the highest power is 4, it's going to be something that looks like this. So either of the two endpoints look like that. We could sketch that in. Again, we do have access just to the graph, so we may as well just use that to make our life a little bit easier. Now, what's important when it comes to sketching this graph is that we just sort of keep everything really nice and accurate. Just have a think about like what happens to the function at these points. So for example, when x is equal to -1, where's the function? Well, if I go over here and go g of -1, that's putting in -1 into the equation, I get out y is equal to -7 when x is equal to -1. So that's way down here, way down here. So I should probably just draw the curve going down like that. Again, make this really clear that that is a stationary point of inflection. It's then going to go up here to my maximum turning point, go down to here. And what's the value of y when x is equal to 2? Well, if we go g of 2, we can see that that's equal to -16. Again, that's way down in the negative y values. So I'm just going to sort of draw the curve going down like that. Making it really clear to the examiner that the function isn't going to pass over here. Now, again, I'm drawing this curve so it's nice and smooth all the way along. It's really clearly just a many to one type function. And yeah, we've got our curve sketched like that. Fantastic. All right, now there was a little typo with this next question, so I do apologize. Hopefully you figured it out. But yes, it says on the same axis, sketch a graph of the inverse function. The inverse for this is not a function, so let's just say sketch a graph of the inverse. Hopefully we can now try and answer the question, but let's suppose this was the question. Of course, the inverse will not be a function because the inverse is only a function if the thing that you're starting with is a one-to-one. This is, in fact, a many-to-one. It fails the horizontal line test, so its inverse will not be a function. But let's just sketch a graph of the inverse. To sketch a graph of the inverse, you first want to put in a line like this along the line y equals x, okay? And then we're going to go about reflecting everything in that line y equals x. Essentially what that means is we're going to sketch, and I'm going to do this in green, we're going to sketch each of these points, and we're basically going to flip the x and the y values. So x and y are the same here and here, because it passes through that line. For this one here, 4 on 3, 0, that was the x-intercept. That is actually going to become the y-intercept. So I can go ahead and put that in over here. So that is 0, 4 on 3. See how I've just flipped the x and the y values around. Then we can just go about sketching in and connecting these things together. So it's going to kind of go up like this. It's like that same line, that same black curve. The green one's the same as the black one, but it's just reflected along this line. Just try and draw this nice and smooth if we can. It's kind of hard to draw with the stylus. Sorry about that, guys. And then that's the stationary point of inflection. All right, let's try that again. So this one here is a touch and go through type point. So there we go. And then it curves around like this, goes down like that, stationary point of inflection like that. And what's it going to do here? Goes through like that, around like that, and then kind of comes down like that sort of thing. Hopefully that makes sense. So that's a stationary point inflection. Yeah, that looks better. Awesome. So we can see how that green curve is basically a reflection in that line y equals x that you can see just there. Awesome. Okay. So this last question is really important because this is what we were looking at this week. Now, when we are describing transformations, so first up, the question says, let H be the result of applying a sequence of transformations to G such that H has a stationary point of inflection at 1, 0 and a local maximum at -1, 1. When you're doing a question like this, it's really important that you get the order right. I would recommend using an order something along the lines of DRT, or you can do RDT. The dilations and dilations and reflections, doesn't really matter which order you do those two in, so long as you do them before the translations. I think it's just a bit easier if you do it that way. So let us try and do that here. Now, in this question, we are told that the transformed function is going to have a stationary point of inflection at 1, 0. So stationary point of inflection, that was this curved bit, right? That curved bit there. That was previously at 0, 0. It needs to end up over here, So it needs to go over here to 1, 0. Okay, so that's where that stationary point of inflection needs to end up. That's one thing. Second thing is the local maximum. The local maximum needs to end up at -1, 1. So let's label that here. So the local maximum was here at 1, 1. It needs to go over here to -1, 1. Okay, so let's go about thinking about this. So first up, I think reflections make the most sense to think about here. So we may notice off the bat that the maximum was on the right-hand side of the stationary point of inflection, but we want it to be on the left-hand side of the stationary point of inflection. So that is actually some kind of reflection, right? We are reflecting this curve so that the stationary point and the local maximum are now on opposite sides of each other. How are we reflecting it? Well, we're reflecting it along this vertical line x equals 0. So in other words, we need to start with a reflection in the y-axis. Let's have a look at what that looks like. Jump over to the graph screen. Okay, we've already got our function g of x. Now, if I was to go and reflect that in the y-axis, we get, I'll tick it. There we go. We get this function here. Now we can see we have successfully reflected that graph in the y-axis like this, and we get this result. Now, as we can see, currently, we now have stationary point of inflection at 0, 0, and we have a maximum at -1, 0. So this brings us a little bit closer to where we want it to be, but not quite. Let's now think about dilations. So how do we think about dilations here? Well, let's think about the spacing between these 2 points that we know. We have the local maximum at -1, 0, and we have the stationary point of inflection at 0, 0. What's the difference between those two values? It's a difference of 1 unit, right? So as in the difference between here and here is 1 unit. In the resulting graph, the one that has the stationary point of inflection at 1, 0 and local maximum at -1, 1, that is actually now going to be a difference of 2 units. So what does that mean? That means that we need to undergo some kind of dilation. And in this case, it's going to be a dilation in the x direction or dilation from the y-axis. Specifically, we need a dilation by a factor of 2 from the y-axis. So what would that look like? What that looks like is we're going to take the old y value, and we're going to say that the new y value is going to be equal to 2 times the old y value. Sorry, scratch that. Dilations from the y-axis. When we're doing dilations from the y-axis, we're affecting the x value. As you can see, we're stretching at the horizontal direction. So let me rephrase that. The new x value is going to be equal to 2 times the old x value. Okay, so we have here this function, y equals, we need to substitute this into y equals into g of -x. So that's the function that we have at the moment, that red function on my CAS calculator screen. To make that substitution, I need to replace x with something. And what do I need to replace x with? Well, if x dash is equal to 2x, then x is equal to a half of x dash, or x dash on 2. So I can just go ahead and replace this with y equals, so I'm replacing x with x dash over 2. We can say that the function is now going to become g of -x dash over 2. So that's the dilation in the x direction, dilation in the y direction, which is, dilation in the x direction, which is from the y-axis. So let's sketch that and see if we got that right. So let me go ahead and type that in. So it should be, sorry about that. Let's go back to the graphing screen and type that in again. So we had our g there. This is now g. So I'm replacing that x. Oops, sorry about that, guys. We're replacing the x with x over 2. All right, we type that in, hit OK, and there we go. We have now dilated by a factor of 2 units from the y-axis or in the x direction. We get this function here. All right, All that remains here is just move everything into position. So we want our stationary point to end up at 1, 0. That stationary point of inflection is currently at 0, 0. So we need to actually translate this graph, and specifically we want to translate the graph g of x, or translates, let's just say translation 1 unit in positive x direction. So when we're doing a translation in the x direction, we're going to replace x with x minus 1, because remember, it's sort of the opposite of what you might think. So we're going to replace x with x minus 1 over 2. And we can see that that is indeed a graph that looks like what we want. So we can see it is has a local maximum at -1, 1. It has a stationary point of inflection 1, 0, ticks all of the boxes, and we have transformed it. So this sequence of transformations does work. Now, it's not the only combination that works. If you have a look at the examiner's report, there are actually quite a few possible solutions that you could have had. So these are a few of the possible combinations you may have used. I've just gone with the first combination here. That was the way that made the most sense for me. That's what I did initially. I didn't just look at the solutions. I did actually look at the solutions afterwards, which is what you should do too. But yeah, this order made most sense for me. But as you can see, you could have done the dilation first, then the translation, and then the reflection, but just make sure that the translation is in the right direction. So for example, if you do the dilation, then the translation, then the reflection, so translation 1 unit left, play around with it and see why that's the case, I guess. But as you can see, the order of these things does matter, and there are only particular orders that are valid solutions. So just make sure that your order is correct. It does say there are other possible answers, but just be really careful to make sure. Maybe you could play around with the CAS screen like I've done here. Make sure that whatever order you've used actually makes sense and does take us from the blue graph there to the pink graph, which is where we want to end up. Anyway, hopefully this video was helpful for you guys. Even if it wasn't, hopefully you could correct it and maybe pick up on a few things. Hopefully some CAS calculator skills. I think Define is really powerful. If you haven't already been using it, get on that. All right, have a good weekend, and I'll see you guys in class.